and let me know when you can see it. Can you see my screen? I lost audio now.
Yes, able to see your screen.
Okay, awesome. So I'll go ahead and just present then. Cool. So Claudiu from Blueprint, thank you for the introduction. What we're going to show here is a solution that we put together in really 2 months. We were asked to start from a wireframe and to build a solution that showed how to scale video processing. And the requirement was to do it in Azure, and we had to also publish a solution at the end of these 2 months in the Azure marketplace. So it was quite a challenge, but happy to have done it. We've learned a lot. We created tremendous value and really showcased our expertise and experience in the process. So quickly, the agenda, I'll do a live demo of this solution. What better way to introduce the technology than actually showing a live demo? Then I'll spend some time on the solution architecture. Then I'll describe lesson learned and talk about what we have in mind for the future as a roadmap. So I'll go straight to the demo. And as I said, the solution is called Nash. It's available in the Azure marketplace. So if you like it, or if the audience like it, they can try it. They can go ahead and try it. If they have a Azure subscription, they can download it for free and then play around with that. But what the application is doing is it's supposed to analyze videos that are stored in Azure Blob Storage and to extract behavioral patterns from that. And let me just show what the app does, because the best way to describe it is to go to the app. So this is one of the deployments of Nash. It has Azure Active Directory as authentication in the front. You can create a new video, or you can look at the existing video. If you have a new video, I'm going to just create one. Let's call it now global demo. And I'm going to pick a video that's already stored in Azure Blob Storage. There's a Blob Storage account that's configured to run with this application, and I'll show you that in a sec. But I'll start the processing in the meantime. I'll pick one shorter video. You get the preview of the video here. If you're happy with the selection, you can go ahead and look at the advanced settings and configure all the behaviors, traffic behaviors that we're going to be extracting, anomalies, and I'll come back to these configuration settings later. And then you can just start the analysis. So by running the analysis, you triggered the processing pipeline. And what this does, it will go to a Databricks cluster that's configured to run, to attach to this deployment. It's configured to process your videos. It can be both CPU or GPUs, and I'll talk in detail in the lesson learned about that experience. You configure the Azure Active Directory, so you allow your user to authenticate, and the storage account where all the videos are going to be stored, right? So considering this was done in 2 months, obviously part of the roadmap we want to attach to live traffic cameras as well, but for the time being, we're just processing existing pre-recorded videos. So what do you get? So in the meantime, while this is starting, this was sent to a cluster in a Databricks cluster that was attached, and there should be a job here that should start. Yeah, it already started. Object detection, and I'll show what the solution does, right? So while you're waiting for the video to be processed, you have a full monitoring pipeline that will tell you what's happening behind the scenes. So there's the video has been broken into segments, and there's processing happening in the cluster. And the first thing that we do in the cluster is object detection, and that's where we use the deep learning model, the neural network models to do the object detection, and then drawing basically the boxes over uh, um, object detected in the videos. And after that, we'll be do tracking, then we'll do video stitching, because segments of videos are being distributed in a cluster. So as they come back from processing, we have to stitch them together. And then we do the insight extraction, behaviors, anomalies, and similarities. And you have this for each segment that's being processed, the exact the metrics and the timelines for what they take to process. And I'll go over the switch to an existing video while that's processing. It'll be a minute before we start getting some insights. And I'll pick one video that's pre-processed before, this one, to show what exactly you're getting in the experience. Now, this is the video that came back. It had the full completed pipeline. You saw there is multiple segment videos and batches, and you have a batch ID associated with really the processing unit in the cluster. And you see that no object detection. This was a CPU cluster. It took 11 minutes, tracking 27, video staging 4 seconds, and so on. So you get this breakdown of processing units. After we complete with all the segments, now as a user analyst, you immediately, as soon as these insights are available, they're being sent to the application. But what we do at the end, we're going through a tracking correction process because now we have the full video stitched together. Now trackers can be corrected if they were lost between segments. Now as segments were computed distributed fashion in the cluster, so separately from each other. So once we have the stitched together video, we can go through that. It's an expensive process, and I'll talk about what we do there. And then at the end, we do another post-analysis where we extract final behaviors, anomalies, similarities. So what do we extract from that? First, we have the object graph. I'll close the monitoring screen. So that's the object graph, and it's in sync with the video. So if you're pulling that the cursor and you want to see a particular area of the graph, the video will sync with that positioning. And the insights, the first set of insights extracted are the behaviors and events. So we're looking at traffic patterns here: oscillation, peaks, valleys, surges, and dives. And they're described in the configuration setting. I'll go back to that. Now, each peak is an increase followed by a decrease in number of vehicles in traffic. Now, and we can configure the delay, and they're all explained, or the rate of change. Now, what's the steepness of the slope? And same with valleys, slightly different. Now, reverse peak, if you will. Surges, dives, oscillations. Then we can configure anomalies. And then finally, the processing. What do we do to fine-tune, provide this knob to fine-tune the level of processing. And this is what you'll see in the object graph. There is a particular process called smoothing, right, that has to happen on the object graph, because it looks like this as a right-hand side panel, and we have to smooth it based on a time scale, depending on what the interest of the user is. If they want to see behaviors across a longer time period, for example, an hour, then obviously the curves have to address that and show you, these behaviors modulated to that time scale. If you're looking for something for events and behaviors within a shorter time frame, for example, 30 seconds, then obviously the curve will have to be adjusted. So the smoothing is different for that. So to be able to identify those behaviors in a smaller time interval, right? So going back to that, that's what you see here. And if I zoom in, for example, I want to see these peaks now in a particular time interval, I can go into the behavior canvas and zoom that in. And so what that will do, it will highlight the actual time interval on the graph. So you see it's here. And actually I can see this particular peak, which is composed of a traffic surge event and a traffic dive event, right? So that's represented in the object graph. And that will allow you for the human eye validation of the extracted insight. So based on these events, based on the object graph, what we also do is anomaly detection. So what we're looking for is also common traffic patterns and outliers, right? So these are all the traffic paths detected now, and there's a clustering algorithm behind the scenes, some machine learning to allow us to detect these paths, and I'll talk in detail in the lesson learned. And the anomaly here in this video is this one track here. There's most of the other cars have different routes, and there's an uncommon route taken by two trucks that happened on this lane earlier, right? So this is what allows us to, you know, our customers wanted to know. Now they don't have the luxury to watch videos all day long. There's multiple sources of videos, but they wanted to see, you know, if there are any anomalies. They wanted to go there and pinpoint it. So for us right now, what's left for us is to actually back reference the anomaly to the time of the video where that was detected, right? That's not something that we have to work on. I have to tell them, when does this happen, right? So when was the anomaly? So we don't have that yet, but that's a work in progress. So those are the anomalies. And furthermore, because analysts are, you know, the consumers of the app, they will analyze multiple videos, and they could be, you know, hours long, days long. They want to be able to see similarity between videos. If there's some similar behavioral patterns in one video, they want to see if there's another video with the same patterns or similar patterns, obviously with a score, that allows them to switch immediately to the other video. Could be a totally different camera in a different part of the country, of the world, that has similar behavior, right? So that's why we're building the similarity score between all the videos, and then you can choose now to watch another video. You click here on the similarity canvas, and you get to go to another video where you can start analyzing again the same, the events, the object graph, and then the anomalies. In this case, different, and the similarity matrix. So that's what the solution does. It's very narrow scoped. Obviously, we only had 2 months to build all of it. The idea is that showcases, you know, all the scalability aspects of processing video and some of the, you know, data science capability we have. But what we expect is customers that are serious about considering this technology and the solution to actually have a more detailed use case with more that would require a lot more you know, intelligence and specialized for that particular use case, for that particular type of cameras, for that particular type of environment, so on. And then I'll go back to my slides and briefly talk about the architecture. So, as we said, the only requirements we had was to build it in the Azure have to publish it in the Azure Marketplace and to build it on Azure technologies. So that's how you see, you know, deployment. The scripts are all, this solution is all containerized, uses, you know, Docker Compose and Ansible scripts behind the scene. And there's obviously a marketplace template that allows us to publish it. Azure Active Directory as a front end for users to log in. Then there's a we call the Nash Linux VM. There's one VM that's a requirement, you know, and that will have these services. We'll have the web console, the management console that you saw, and 2 services, a JVM service and a Python service, and they do all these things, you know, anything from orchestrating the jobs to all the analytics that happen post-processing. And then we're using Elasticsearch to store all the detected insights, you know, events, aggregations, behaviors, everything that we'll need to use for reporting. In the future, analysts could overwrite the model, and they could take notes and annotate and tag various scenes in the video. So then we will use Elastic to allow them to search, basically building a rich semantic layer on top of the solution. And then that's inside the VM, and attached services are an Azure Databricks cluster where we do all the object detection and the classification. By the way, the solution was only trained for trucks, buses, and cars. We on purpose ignored people and bikes or smaller vehicles. We just fine-tuned it for that particular use case. Blob storage for storing all the videos. Postgres for configuration. The solution is somebody who downloads, they get another product from us, Conduit. It's a data virtualization product that allows you to import from the across multiple videos, and that's something that should show here. So if you want to see Now anomaly counts across multiple videos, or you want to see the actual raw like object count. Now before smoothing, this is the actual raw object count, or any analytics you want to do across multiple videos. Now, what's outside of the solution, you can do that. Now you can report from your tool directly against Elasticsearch, but for that you need a product, and we bundle this product in with the video solution for somebody who downloads it. So that's what Conduit is. Any questions so far before I go into lessons learned? I guess I have to check the chat.
I have a question, to ask question. Scaled ML is one of the approaches that was taken by a company called Matroid, connected to Stanford University. I've seen their presentations, and I know the principals and the scientists. That's one of them. And H2O also, I've seen their presentation working with the NVIDIA. Anything different from they are doing that you are doing better and things like that?
Oh, I'm not familiar with them, so I wouldn't be able to answer that question, because I'll have to know what they do, what's their approach. But I'll answer this last question. The most common use cases users wanted, they want to see. Oh, that's a good question. Actually, I should show you. They wanted to see in the future. For anomalies, they wanted to see accidents or particular size-based anomalies. If it's a particular bigger vehicle, like a big bus or a tank, who knows, strolling through an intersection, they wanted to know about that, because it's obviously an anomaly for the type of vehicles in that particular intersection. Or they wanted to be able to override the extracted intelligence, and then say, okay, this is not an anomaly, this is actually a common path, or this is not a behavior I'm interested in, or I am interested in more. So they wanted to us to learn basically from the user interaction. And I'll show you one video. This is a pretty cool. This is the animated video, and there's this individual who has he's overexcited. He does a donut in the middle of the intersection, and the anomaly detector actually points that. So this is the video that we started. So this tells me that, okay, there's more insights coming. It's still processing. So I'm going to go to the same video that was processed earlier before this guy, and then I'll show you the anomalies here. And I guess no, it's not working. So oh, okay, it's still processing. So I have to pick up a video from that I processed before, because the anomalies are computed at the end. Let's see, section 4. I might have a demo blip. Yeah, looks like I do have a demo blip. So I was going to show but I have that in the slides. So I was going to show you basically this picture. So the detector, uses the tracking to follow this donut, and actually identifies it as an anomaly compared to all the rest of the common paths in the traffic. It's possible that it's still it's computing similarity for all videos, and then it's recomputing anomalies as well. So that's what happens when you do a live demo. You get some of this. So back to the lesson learned. Lesson learned on the infrastructure side of things. So we're using Azure Databricks, as you saw, CPU versus GPU, and then this is what we noticed, right? Obviously, we want to use GPUs now, because we're noticing that for object detection, it's 40 milliseconds per frame versus 24 seconds per frame, right? And these are clustered at price parity. So the two clusters, obviously, big difference in performance for object detection. Uh, there's one key aspect here. If you want to run your own libraries, which require now deep learning models and computer vision libraries and so on, you have to load your own image now into Azure Databricks, and that's not today available on GPU clusters. So are able to do this now, to load our own images. You see his blueprint, because we're working with the preview release edition of Databricks. Now they allow us to use it, but it's still not released. So as soon as they release it, we'll be able to now offer support for GPU clusters, and obviously that's what we want to use for object detection. And that's on the really truly on the infrastructure side. We have some numbers here for particular videos. Now we're looking at the spend time, the latency of the jobs, and you see the Kuala Lumpur video took like 80 something minutes versus just now a fraction of that on the GPU. And you see the GPU clusters are obviously better performance at price parity, but we're not seeing the desired increase there in performance. Now I expected from 24 to 40 milliseconds, there is like 600 times faster. And we're not seeing the same delta, the same difference in overall latency. And that's because we're not doing batching. Basically, we're processing right now in this version that's released, we're processing one frame, detecting object in one frame, and immediately do the tracking on the same frame. And tracking is still done on CPUs by us. So we can do detection on GPUs, but the trackers are running on CPUs. So that context switching, that where we lose performance. So we're looking at right now to speed up, basically batch multiple frames to do detection on them, and then to continue tracking on the same batch. And that's going to avoid that context switching, and you should show us now performance increases that are closer to this now individual frame by frame comparison. On the object detection front, now what we have right now is one of the Gluon models, and we're using MXNet. That's the Python library for detection. But we are now experimenting with efficient depth, which is a different implementation, and that's only available through PyTorch. And I have a comparison here of neural network models. They're all trained on the same COCO data set, and the same metric is used, mean average precision. If you look at this red line, these are the efficient depth architecture models, and we're using D1. The better the model, the more expensive it is as well. But if you move up towards D6, D7, which is probably the best model in that architecture, the floating operations per second rate doesn't increase as much. And so that's what we're looking to release next, these models. Those are running on the GPU clusters right now. And that's how we used to do the benchmarks. But in this release, we started with the ResNet model. They're coming from the Gluon library. And you can see, obviously, that you really pay a price for better quality now in terms of processing. So that's why there's a comparison here between the two models, the faster RCNN versus efficient depth, which is new architecture. And you can see how efficient that outperforms at all levels now, at speed, at memory consumption, the disk consumption, and even for the same precision, for the same median average precision, you get now a lot of performance improvements. So obviously, we're going to move towards these efficient depth architecture, and hopefully on GPUs if it's available. But they also outperform the Gluon models on CPUs as well. So that's what we learned on the detection front. We're also looking at training our own or bring your own train model, and it's very much dependent on the quality of the train set. And to this point in time, we have mixed results, but we still haven't had a good data set to train on. So training your own model is expensive, and better likely we'll stick with the efficient pre-trained model and fine tune around those. Then on the tracking front, what we use today in the release, we use the Kalman tracker, but it's customized. remember that correction that we do at the end. Let me show you that again. If you look at that correction segment at the end, the tracking correction, it is doing that, and that's expensive, obviously, to pay. Now it's 12 minutes for the total duration of 30 minutes. So from the 30 minutes, 12 minutes was just this tracking correction. So that's why we started looking at a different tracker, and we found Fairmont's a different tracker. We're having like 10x speed ups on CPUs. We haven't moved tracking to GPUs yet, but it's a much faster tracker, and generally better performer. There are videos where it doesn't perform better, so there's still some issues with that thermal tracking. It's a matter of us fine-tuning all the parameters available for the tracker. Or what we're thinking in the future, to have a mix and match configuration. We might combine detectors and trackers to whatever works best for that particular type of video, right? So that's always going to vary. So that's why we're going to implement this flexibility in our configuration, so we can combine detectors and trackers, because they're completely independent. And yeah, so that's the tracker. Let me go back. Next slide on lesson learned. On the behavioral patterns, now I mentioned earlier, we do time scale smoothing, because if you see here, if the time scale is 1 second, then you see the orange curve. What I want to see more variations in my object graph versus the 7 seconds, where obviously the curve has a different amplitude, because I'm looking at changes and variations in my object count over a longer period of time, right? So that's why you go into the solution, and you are configuring the processing here. They're specifying the time scale, right? This is 1 second here. That allows, if you have a longer video and you want to see what happened over like half an hour or an hour time units, then you're going to have to change this parameter to see that representation honor that setting. So that's on the, and then we use now NumPy, Hanning smoothing with the low pass filter approach to build these curves. On the anomaly detection, the team started with dbScan, but then they set up with agglomerative clustering, and this is for computing. So tracking is very important here, and the quality of the tracker really influences the quality of the detection. And on the, because it's really close to finish, and then the similarities, we look at right now with similar behavioral patterns, only motion-driven behaviors between two videos. That's how we compute. That's how we calculate the similarity score between them. And we look at the overlapping behaviors and events and their counts. In the future, we were asked to also look at the footprint, the environment. They want us to compute the similarity just solely looking at the environment and ignoring the motion-driven behaviors. If the intersections are similar, the building sites are similar, they're positioned in the same way, they want us to build that score as well, right? So right now, when we look at similar videos, we're just looking at really those traffic patterns that are similar between the videos. So that's how we compute them. And then let's see if I get maybe I do have the anomaly, so maybe there's something wrong with that one video. But anyways, that's what happens when you do a live demo. You might get that hiccup. Let's see if I can find. Anomalies. No, not yet. Cool. I guess I'm not going to show you the donut here. It's detected. So we have something for my engineering team to work on. And that's all I have. Now in the slides, I have some links at the end with the resources. The Glue-on model is the efficient depth architecture, and the link to the marketplace offer for this solution. I repeat, you can download it for free if you have an Azure subscription. Play around with that. We'd love to to get some feedback, and why not hopefully take it into a direction where we can develop a special solution on this core technology and architecture. Okay, so I'll take some questions here.
There are questions there.
Okay, so I explained
starting
the
at.
Okay. I imagine the customer uses that for synthetic data or script in real-world corner case, or at least knowing what to search for. Yeah, and we don't know we don't know our customer videos, how they are. I mean, we try to use various traffic cameras from different sides of the world, even computer animated ones, even real ones. But really, until we actually run this against their real videos, we're not going to know how well we perform, and we're ready to to adjust. Can you show slide 4 again, please? Sure. Slide 4 is here. Yeah, I will share the slide, by the way, with Lena at the conference owners. So this is just talking about the lesson with Databricks, with the CPU, GPU, and the detection of the tracker. I'll share that later. Another question here I have. Are you paying for the Azure bills, or is the end customer? Do you have much incentive to investigate efficiency? If so, what were your main findings? Yeah, so it's available in the marketplace, but it's installed by the customer in their own subscription. So they don't pay for the solution. It's a free license of the solution, but the cost of the VM and the attached cluster is incurred by the customer. And if the yeah, we are investigating efficiency at all levels, as I described. We're looking at the processing efficiency. That's why we're doing all these measurements now between detectors and the trackers. We're looking at both the runtime performance and the analytical performance, right? We care about both, and we're committed to continue that work on the existing videos that we have, right? That might change as soon as we go and run against and we can wait to actually do that, to run against the real videos, and see how our algorithms actually work. Very likely we'll have to specialize and fine tune them. Which parts were done in Spark? How did the Gluon model integrate with Spark? So, good question. Object detection and tracking is done in the cluster. And if there's a GPU on those nodes in the cluster, then we use, in this release, we use the ResNet model to detect objects. And then we draw the bounding boxes and we do the tracking with the CPUs on the same nodes. How we integrated the Gluon model with Spark, I'll go back to this. Basically, we are running our own Docker containers, pushing them into the cluster. You see this blueprint, Azure CRIO. So that's our own containers. And they do have all the libraries required for the models for detection and the trackers and the OpenCV library and so on, everything we need to run in the cluster. I hope I answered that. Slide 4, any insights why is quality train set dependent, didn't cover enough corner cases? Yes, we just started training, and I have half a resource, basically somebody who's part-time working that right now. And first we wanted to explore the models, the parameters, and then learn how to train them. And we are doing that right now. And like I said, we're seeing mixed results. And one of the culprits is the quality of the train set. We don't have the COCO data set. So we are using our own labeled data, basically. We have to label those videos ourselves. So that's an expensive process, but we're still going to pursue that. We're so happy though with the efficient depth models and the performance that very likely we're going to lose that motivation to train our models very fast. So I think we're almost up. If there are any more questions, I'm happy to take them now. If not, you can reach me. you can reach me, individually if you want to talk more. Reach me on LinkedIn, and I can do more, deep dive and follow-ups on this. But thank you so much for
Fantastic,
watching.
Claudio. It was a very good presentation with the demo. We like it, and it's very, very enlightening to a lot of us.
Let's see if the
I
camera works.
appreciate it. Thank you.
Thank you.
Okay, and now yeah, thank you. Now we have the mentoring sessions starting. In the chat, there's a link that has been posted. You can go to that and pick topics, AI in finance or how to get into Stanford.